Okay, I think that's working. I can never really tell. One time I thought I was recording an entire lecture and didn't even record at all. It was so irritating. Okay. So we wrote our dissolving equation. I want to set up my expression so I can see what all is needed and to what power things are taken. I know it seems like a redundant thing, but you just need to do it, okay? All right. I'm trying to find the solubility, which means I'm trying to find the concentration. And what that means is the value of x. I fill out my ice table to remind myself that x is added by a factor of 3. I'm sorry, A. A is increased by a factor of 3x. So now, let's substitute oh, I shouldn't have used x. That's a little confusing. But, wait a minute. I'm doing more work than I need to. Back up the truck. Didn't have to do this at all. I mean, I guess it's fine that I did. But basically what we need to do is this. I'm thinking the wrong way. We know the solubility of the compound A3X, right? So the real question is, for every A3X, how many A's are there? 3. So 0.045 molar is the concentration of A. My bad. That's what goes in here. We need the concentration of X. For every A3X, there's just one of those. And that goes in there. Okay, I didn't need a nice table at all. Oh well, it didn't hurt though. So now let's see what we get. You guys tell me what you get. Go run the numbers. That's right. All right. Did that turn out okay? Did we all get that? All right. That would be exhibit A, right? First type of solubility problem. Let's go backwards. Let me give you a KSP value. So, KSP for zinc hydroxide is 3.0 times 10 to the minus 16. What's the solubility? I'll give you guys some lead time. See if you can come up with it. Let me know if you have the answer. That's it. Yep. Okay. So all right. This ice table would look like this. So 3.0 times 10 to the negative 16th is equal to quantity x times quantity 2x squared, which means x is 4.2 times 10 to the minus 6 molar. That's a pretty small molarity, 4.2 times 10 to the minus 6th. Imagine a solubility curve like the ones that we showed you last unit, right? And this was like it was in grams per 100 milliliters, right? But even if we did it in molarity, right? So like, let's say that this was 0. Let's say this was 0.1 molar, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, and so on. And this was the temperature. Where would this fall? Let's say that this is at 20 degrees Celsius. Right. It would be here. And any of the other solubilities that we solved for, like all of last week, did you notice they were all like 10 to the negative 4, 10 to the negative 3? They would all be like down here. Right? Again, remember the solubility rules, how we would say they, what's going on? How we would say that, something is soluble. All nitrates are soluble. All alkali metal compounds are soluble, right? And then we would say that all hydroxides are insoluble unless they're with alkali metals, right? All carbonates are insoluble. What we mean by that, when we say it's insoluble, is it means it's got a really, really, really tiny solubility. So the truth is, everything can dissolve to some degree, but some far, 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 far less than others. If we're calling something insoluble, that means the solubility is like this. It's tiny, right? Whereas with sodium nitrate, I can make like a 3 molar solution of sodium nitrate. It's really soluble. Sodium chloride is really soluble. So those solubility rules that we went over, that's like an overgeneralization to make things simpler. But when it comes down to it, when we need to find actual concentrations, we use equilibrium. Okay. It's kind of like, when your first box of crayons, there's like 8 colors. There's red, orange, green, yellow, blue, purple. And then by the time you get to 5th grade, you get the 64 colors, and all of a sudden there's like 8 shades of red. Remember how mind-blowing that was the first time you saw all those different reds? Well, it's like this. It's like you're being told something is soluble or it's not. Well, the truth is always somewhere in between. Okay? I don't know if that was helpful. Okay, let's work out another problem. We will continue to use zinc hydroxide because we already have the KSP value here. I'm going to mix 2 solutions together. I got a test tube. There's 35 milliliters of 0.0012 molar zinc nitrate. And this is going to be mixed with 35 milliliters of 0.004 molar sodium hydroxide. Again, the KSP for zinc hydroxide is 3.0 times 10 to the negative 16th. Okay, Of course, the question is, what are we going to see? Are we going to see precipitate, or are we going to not and have this remain dissolved? So this is a more involved problem, but it still helps if you start it the same way that you started all the others. The KSB value, after all, that we are referencing is based on the fact that we expect zinc and hydroxide to be part of the precipitates. I know this for two reasons. I know this because all nitrates are soluble, and we wouldn't be using an equilibrium for something like sodium nitrate. But also because the KSP for zinc hydroxide is there. If it's there, then that's the one you use, right? That's the one that's relevant. So, we do not have initial concentrations, however. Like, we don't know. What I mean is we don't know that this is equilibrium, so we're going to be solving for Q. All right, so if I'm going to be solving for Q, I need initial concentrations of zinc and hydroxide. So I have to figure out what those concentrations are. What can we do from here, guys? How do I go about finding the concentration of zinc? Yeah, DJ?
You can find the number of moles by multiplying the milliliters with the concentration.
Yeah.
And then from there, find the actual initial concentration.
Okay. So let's do zinc first. Here's what we know. We know that there are 35 milliliters of zinc nitrate, and the concentration is 0.0012 molar. So 4.2 times 10 to the minus fifth moles of the zinc nitrate. Yeah, Alan.
If we needed the molarity of the nitrate, would that be 0.0024, or would it still be 0.0012?
Correct. If we needed the molarity of nitrate, it would be 2 times the 0.0012.
Right.
Yep. All right, so I got moles of zinc nitrate. It's not zinc nitrate that I need, it's zinc. All right, but that is the moles, and brackets means molarity, right? So we actually need the molarity. So what do I do next? Yeah, the total volume. Everyone see that? 35 milliliters, 35 milliliters. That's going to be 70 milliliters total. So we're dividing this by 0.07 liters. Yes?
How do you know that it's 1 mole of zinc?
Because look at the formula.
Which one? Oh, okay.
I'm sorry, not that one. Here, this one. In the formula of zinc nitrate, there's only one zinc.
Okay.
Yeah. Okay, so the concentration of zinc is 6 times 10 to the minus 4 molar. Okay. That would go in there. So we need the other one. So for hydroxide, volume times molarity. This time it's 0.004. Of course, there is one sodium in every one hydroxide in every sodium hydroxide. So 1.4 times 10 to the minus 4 is the moles of hydroxide. Again, we need this as molarity. And that's our second concentration. All right, decision time. Do we see it precipitate? There's a big difference. It's not even close. Was that a yes or a no? Yes. Yeah, look how big it is. 2.4 times 10 to the negative 9th compared to KSP, which was 3 times 10 to the negative 16th. This is definitely going backwards, and you will definitely see it precipitate. So this will then start to look like a snow globe. All right. Your turn. Let's give you a different compound this time. The KSP for calcium chromate. 4.5 times 10 to the negative 9th. We have 50 milliliters of calcium nitrate, molarity of which is 0.0015, added to 50 milliliters of ammonium chromate solution, concentration of which is 1 times 10 to the negative 5th. Figure out if it's going to precipitate. This one was a closer call than the other ones. All right, hopefully you got a Q that was pretty close to K. Did everybody see that? So what do we think?
3.75 times 10 to the negative 9.
It is. Which means
It goes right to no precipitation.
no precipitate, yes. Okay, let's work it out. So, this is a simpler solid. It just gives 2 ions. So nothing is squared. All right, you just need to find the concentrations of each. So, for the calcium, did it again. Wouldn't want to confuse my liters for twos. All right, so we got 7.5 times 10 to the minus 5 moles of calcium. I know that this calcium, only one calcium per formula, because when I look at the formula, I only see one. All right, the volume, our total volume of our solution is 50 plus 50, so 0.1. So molarity is 7.5 times 10 to the minus 4 molar calcium. All right, our chromates. All right, we have our 2 ion concentrations. So plug them in. Q is 3.75 times 10 to the minus 9th. Q is slightly less than KSP, because if you recall, KSP was given at the top, 4.5 10 to the negative 9th. So this reaction will go forward, and we will see no precipitate. So actually, there will be no snow here in the globe. Clear day. Kira, question.
So for the fact that there's 2 moles of ammonium, does that matter or no?
No, because that's a spectator ion. That is not part of the solid equation,
Okay.
so you ignore it. How are we doing? All right, good. So, while we're here, let's review, just run through the main points of the notes from the top. All right. The definition of equilibrium is when your forward reaction rate equals the reverse reaction rate. Okay. The thing to remember is that because this is what we call a dynamic equilibrium, that reactions are still happening even though it looks like things are no longer changing. Okay. So, for instance, in our lab, once we mixed those the thiocyanate and the iron together and got that orange color, the orange color, once we made it, it looks like it just stayed the same, but the reality is there's the product breaking up and there's the product forming equally. And so it's what we call dynamic equilibrium. When we look at a graph, there's going to be different rates of change. Like here, notice how the amount of change here for the reactant and the amount of change for the product, they don't seem to be the same amount. That difference in change is based on the mole ratio, 2 to 1. We expect the rate of change for the product to be twice that to the rate of change for the reactant. If this was a 3 here, then it would be a difference of 3. Like you'd have, plus 3x versus minus 1x or vice versa. Okay, so when you're reading graphs, the change in the graph should be reflected based on whatever mole ratios there are. If it was 1 to 1, then they would change equally, and so both lines would change by the same amount. So your equilibrium quotient is your ratio of products over reactants. If there are coefficients, they become exponents. We've done a lot of this. Don't need to talk too much about that. Remember what it means. If the K value is really small, that means the reaction favors the reactants. In the solubility problems that we just did for the past 20 minutes, would you say those solubility reactions are product favored or reactant favored? Reactant favored. Look how small they were. They were far less than 1, right? So, whereas we had a lot of gas reactions on our, I think it was worksheet 1, where you got a bunch of gas reactions, the KQ values given to you were like in the hundreds. Gas reaction KQs tend to be high. Okay. Let's see. Rules for equilibrium constants. If you reverse a reaction, then the new KQ is the inverse. Rule number 2. If you multiply a reaction by some factor, the KQ is raised to the power of that factor. Rule number 3. If you add two equations together, the new equilibrium constant is going to be the product of the two. Sometimes this is straightforward, sometimes it's not. Sometimes you have to do a lot of switching around to make something work. So while I mention that, here, let me give you another one here. I'll do it in green so it kind of stands out. All right, so let's say I have this. X goes to Y. The KQ is 4. Two W goes to 2Y. The KQ is 10. I want to know what the KQ is for this reaction. In its current form, I cannot just add these together. There's a couple of things I have to do. What do I need to do? Flip it, okay. So let me rewrite this. 2y becomes 2w. And so this KQ is now 0.1. Right, 1 over 10, 0.1. Okay. I still can't algebraically add these yet. Yes. So I'm going to multiply this reaction by 1/2, which means I have to take the 0.1 to the power of 0.5. So that becomes Y forms W . 0.5. 1/2 power, right?
Oh, okay.
Sorry, yeah, I wrote it slightly differently. I'll write it the way same way I wrote it. Okay. So 0.1, the square root of 0.1 is 0.316. So now, finally, if I take these two equations, I can add them. And by the way, when I say add them, maybe I'm skipping a step here. The reason why I'm canceling Y is because when I add these two reactions, it's going to look like this. It's redundant. Do you guys see that? That's why I'm canceling y, because it appears on both sides after we add them. So now I take the product of the case. Four times 0.316 is 1.26. So if you ever have to add two equilibrium reactions together, you might have to fiddle with it a little bit before you can add them. And if you change them a little bit, you have to abide by the rules. If you flip it, if you multiply it, you have to keep those in mind. Okay. Heterogeneous, homogeneous equilibria. So heterogeneous equilibria is when you have more than one states. The main point of stating this is that you cannot use solids and liquids. That is the point you're getting across. Solids and liquids do not have measurable concentrations. Gases, fine. Aqueous, fine. All right, so equilibrium calculations. This is what we've been doing, right? Rearrange to solve for the equilibrium constant. That's the first type. Or find equilibrium concentrations if you're given the equilibrium constant. Right? Sometimes ice tables are needed, sometimes not. It depends on what's being asked. Don't forget about coefficients, because coefficients change how much your change in your ice table changes by, like here. Whoops, didn't want to do that. Like this, 2, 2, 2, right? Solver. Are we still having any problems with solver? Have we ironed those out? The main thing I still saw on some of the homeworks from last night is you might solve for a value of x, and it would read like 4.89. And 4.89, let me tell you something. The value of x will never be larger than 1. So if your number says 4.89, that means you got to scroll all the way to right. That means you're not seeing the exponent. It's really 4.89 times 10 to the minus 4 or something like that, right? Scroll all the way to right if you have the older calculators. If you have the newer one, it's not going to be an issue because it gives you the whole thing. So just be careful, right? Your x value will never be greater than 1 in any of these problems. We skipped that part. Solving for Q. You guys know what Q is and what to do with it, right? Q is how you determine if a reaction is going forwards or backwards. You have to solve for it. If Q is too large, you have too much product. That means the reaction must go backwards. If Q is too small, you don't have enough product, then it will go forwards, meaning you will add to the product side. Le Chatelier's principle, right? Any kind of systems that's at equilibrium will try to get back to equilibrium in spite of whatever stress you cause. So these stresses can be you add something, you remove something, or you change the volume or pressure, but that only affects gases. Remember, if it's gases, you have to pay attention to how many moles there are, right? Because the changing in pressure, basically what you're doing is you're determining how much space the reaction has to exist in. So if you squeeze it, it has to exist in less space. This first one here would go to the left because the left side needs less space. Okay. Temperature. Pay attention to whether the delta H is positive or negative. If it's positive, it's endothermic heat as a reactant. If it's negative, it's exothermic heat as a product. Remember that changing temperature is the only thing that can change the equilibrium constant value. And then that brings us to KSP, which we did a bunch of today. All right. There are other worksheets which we just did not assign, but here's a good one. Homework 6.5 is the long type question like the one that we just did, where you have to start from scratch and figure out what Q is and determine which way it's going to go, right, when you mix things. So that's a good one to do. The answer keys to all of these are open, so you can check them as you go. The review, there's a unit review. There's 2 of them, actually, so you can go through and do those as well. Remember that we did skip one topic. It's called common ion. So if you get to a question that refers to a common ion, you just skip it because we didn't do it. And your homework is the practice test, per usual, okay? All right. What is there anything you want me to go over? Okay, well, if it doesn't come to you immediately, that's fine. Why don't you take the time? You got about 18 minutes or so. Work on either the practice test or work on the extra practice, the homework 6.5, or one of the review sheets. We are not going to have a lab quiz because I forgot to give it to period 6 yesterday. And it would be unfair to give it to you now.
I'm not complaining.
So, yeah. You all did great. Hey, did you hear? All right, now let's